In Chapter 13, we are going to be discussing what we call vector-valued functions. So, ignoring any time that you use complex numbers, all the functions that you've been working with throughout college algebra, trigonometry, calc 1 and 2, those are all what we call real-valued functions. A real-valued function, you could say a function f, takes in a real number and outputs real numbers. So here we're kind of not really talking about what we're putting into it. All that we're going to be putting into these functions are going to be real numbers, but we're talking about what is the output. The output here is this real number. A vector valued function is similar. We are still going to be putting a real number into it, and I'm going to use r because that's usually the notation we're going to be using here. Technically, this is a boldface r to denote that it is vector valued. But we put a real number in and output a vector, not a real number. Now this vector could be in 3 dimensions or 2 dimensions or however many dimensions you may want to be talking about. And this is not the first time we've seen this. Recall back in section 12.5 when we talked about lines, the very first thing we did to give it equations for those was derive a vector formula for it. We had a formula r here being the vector x, y, z, equals r naught, which is r naught comes from a point on the line. Then we had t times v, where t is just a real number, and v is some vector along the line. In other words, since r naught and v are given to us, or at least we find them before we start writing down the equation of the line, really what we have here is a vector valued function where we plug in the variable t and we output whatever the whatever the result of this scalar multiplication and addition gives us. So we put in a real number, we get out a vector. Now, we say vector valued. The book also refers to these as vector functions. I'm more comfortable just saying vector valued functions, so that's what I'm going to do. There are a few other things that we could call these, but I'm just going to stick with vector valued. The book also kind of specifies that vector valued functions give us vectors in 3-dimensional space. That is not a hard, fast rule. In fact, the book even breaks that rule when it comes to their exercises. They kind of just in say like problem 7, for instance, they throw a vector value function that gives vectors in 2-dimensional space, even though they haven't actually introduced 2-dimensional vector value functions in the text. So they just kind of expect you to be able to roll with it. It's really just because vector value functions are, in fact, a lot easier to work with than you might expect them to be. I should also note before we continue, when we dealt with real valued functions, we almost always use variable x. Not always, but it was pretty much always we call the variable we put into the function x and the variable that we get out of the function y. For vector value functions, because the vectors are going to be vectors in x, y, z, it's usually better to pick some other variable. So the kind of the standard one to pick here is t. That's pretty standard thing to use. If what we're working with has something to do with angles or is using mostly trigonometric functions, we might use theta instead. And in a couple sections, we will also be looking at some situations where the variable s is frequently used. But in a technical sense, the variable here doesn't really matter. I'm going to stick with t, except in a few cases, just to kind of keep it standard. So why is it so easy to work with vector value functions? Well, it turns out that when we look at a vector valued function, say r of t, we can always actually break this r of t up into x, y, and z parts. Basically, if we have a vector valued function r of t, there are going to be real valued functions f of t, g of t, and h of t. Now, of course, here I'm working in three-dimensional space. If we work in 2 dimensions, we'd only have f of t and g of t. But we basically, every vector valued function corresponds to a collection of real valued functions. And a lot of the things that we want to be doing to this vector, we actually can do directly to these real valued functions. So we'll see that a lot when we get to limits, to derivatives, all that kind of stuff. In fact, with integrals as well. But we'll get to that in the next section. We can also write this in terms of I, j, and k. So say f of t times I, g of t times j, and h of t times k. And most of the time, I'm going to assume that we can have both the r and the fgh. These are called the component functions. Because they literally just come from the components of the vectors that come out of our vector valued function. I'm almost always going to be writing my functions using the component functions, and the book does this pretty much exclusively as well, because that allows us to use the functions that we're more familiar with. So just kind of some examples of possibilities here. You might have something like r of t is the vector with components 3t plus 2 and t minus 5. That is a vector valued function in 2 dimensions. You pick a t, it spits out essentially a point or a vector in 2-dimensional space. We can have something a little bit more complicated than that. So here we're going to have 3 components. The first component is t squared. Second component is square root of t. Third component is ln of t. Of course, here the domain of this function is not all real numbers. For example 1, it doesn't matter what t we pick, we are going to get a vector out. For example 2, obviously the square root and the natural logarithm, they don't really work well with negative numbers, and the logarithm doesn't work well with 0. So example 2 has domain all t that are greater than 0. So we can still talk about domains just like we did before. It's just what values of t can make any sense to be plugged into that function. Problem 3, or example 3, you can say r of t is cosine of t, comma sine of t. And that's actually a very familiar curve, but we'll actually, or they'll turn into a very familiar curve when we actually get to turn these into curves instead of just functions. Talk about how we might graph such a thing. And 4, we can start with the same 2 component functions from our 2-dimensional vector value function in 3, but then add on in a third component. You're going to do t over 2. That is a 3-dimensional vector value function. So I got to mention we're going to be graphing these things because we want to get a grasp on what these vector value functions are doing. So if we, actually let me give another page. So if we are looking at a vector value function with our component functions, what we'd like to do is treat this not as necessarily giving us a vector, but kind of turning these into points. So the point where the different coordinates are given by f of t, g of t, h of t. Or in other words, since this is x, y, and z, we're really turning these into 3 different equations. So where x is equal to f of t, y is equal to g of t, and z is equal to h of t. If you remember from back in chapter 10, and kind of extending this into 3 dimensions, what we have here is a set of equations called parametric equations. We kind of mentioned this already when we talked about lines. Parametric equations, we have a parameter t, or whatever parameter we want to pick. We put that parameter into the functions, and it output pops a point. And what the graph of these points are, if we just keep plugging in numbers and plotting the points that we get out, we're going to get curves. The graph of that's going to be a curve. The book is referring to this specifically as a space curve because they're focusing mostly on the 3-dimensional stuff, but there's no reason why we cannot do this with just a 2-dimensional vector value function where we just wouldn't have the z equation. We'd have 2 equations for x and y, and the result of that will graph as a curve in 2-dimensional space. Now, of course, we could always try to graph functions like this by plugging in values and trying to get an idea of where we can put those points. But since we do have a computer, we have GeoGebra, in fact, and that's what we're going to be using to actually get good graphs of what these look like. And I'm going to go ahead and look at the four vector value functions that I gave you back here. So let's plot these 4 curves. So example 1 was just a 2-dimensional curve. And so we're going to plot this in 2-dimensional space. And to do that, we are actually going to need to use a function in GeoGebra. It's not going to be just as simple as typing in a formula. We're going to actually have to have a... let me actually write it out here. GeoGebra has a way of writing this for parametric equations. It starts off with just curve, and then in parentheses we'll put whatever our formula is for f of t. And here actually we could pick a different variable if we want to. I will show you some examples of that in a moment. We put whatever our equation is for g of t. And don't write this as x equals f of t and y equals g of t. Just write the f of t and the g of t. If we do have if we are working in 3-dimensional space, we go ahead and put our h of t here. If we're not working in 3-dimensional space, GeoGebra will recognize that you're only putting in 2 functions here instead of 3, so you don't really have to specify. But what you do need to specify is you have to tell GeoGebra what variable you're using. If you're using a variable t, you need to put t as your next thing in here. If you're using the variable theta, you need to put theta here. And you can put theta as just typing out theta. If you're using whatever other variable you want, you put the variable there. Then it also needs 2 more values. You need to tell it what values of t to plot. So if you want, let's say, I'll just write it as t start and t end. Basically, what starting value of t do you pick? What ending value of t do you pick? Of course, if the domain is given to you, if you know that you're only putting in t's on a domain of 0 to 1, you could put 0 and 1 there. If you know that it goes off to infinity in both directions, you still need to put values. GeoGebra just kind of requires that. But just in those situations, you can just pick a big T and pick a really small T and a really big T that you expect it to go off the graph. So let's actually start with our first one here. So here is 3t plus 2 and t minus 5. Of course, that does have domain all real numbers. We can plug in whatever t we want. So put in curve. And if you don't remember what the actual format of that is, GeoGebra will remind you. It'll kind of put in there what you need to put. So this first suggestion here It has two expressions for your f of t and g of t, and then it doesn't have a third expression because this is for a two-dimensional curve. The second suggestion here is for a three-dimensional curve, and you can actually click on that and it'll go ahead and put these in here for you to replace them. So again, my first expression was 3t plus 2. My second one was t minus 5. My variable that I chose is t. And then I'm just going to pick, say, well, actually, let me show you when I pick smaller numbers. Let's just go 0 to 1. And when I plot that, I get this line segment. You can kind of, maybe you could remember that what we have here is the equation of a line, just with, in this case, a vector along the curve of 3, 1, and passing through the point 2, negative 5. But because I only pick from 0 to 1, it actually only plots a little bit of it. If I wanted to see more of the line, I would go ahead and allow t to be on a wider range of numbers. Let's just say from negative 10 to 10. That will show me just about everything that I need. Now, one other thing that we like to do with curves is specify what direction the t's are increasing. So a t here does not necessarily correspond to any points on our axes. So if I put in t equals 1, I'm not getting out the point that's just below the 1, because x is not equal to 1 when t equals 1. In fact, x is equal to 5 in that case. But what GeoGebra does allow you to do is, if you recognize what the name that it's assigned to it, so it called it A, and you could actually, if you go into the properties of this, you can give it a different name if you want to. So maybe I'll call this my line. I don't know. GeoGebra doesn't just treat that as a curve here. It actually does treat it as a function. So I can type down here my line, and then in parentheses I can put in what value of t do I want to put into my parametric curve. Let me actually expand this so you can see it a little bit better. So let's plug in 0 first. And it gives you a point. This point is the point on this line that has a parameter of 0. When I plug in 0, I get that point. If I want to plug in a different point, that's my line 1. So this is where this is the point on the curve where my parameter equals 1. And if I really wanted to specify those, I could, if I wanted to draw this picture to show to other people without having to explain it all the time, I could say this first point, this is where t equals 0, and then have it show that caption. So that's where t equals 0. For point B, this is where t equals 1. And you can show that. So you can kind of see that if you were to plug in bigger and bigger values of t, you actually get points further along this direction. If you put in smaller values of t, you get points further and further along that direction. That can be useful information if this is showing, say maybe this is showing the position of something at a given time, and you want to specify at what time is whatever you're letting move around, at what time is it at any given point. The book actually likes to put in arrows showing what is the direction that the t's are increasing. I don't really know a way of doing that in GeoGebra, having it actually display those without getting really complicated stuff. So I'll just kind of talk about it and maybe show some points that will kind of guide you along where things are going. But I can't really put in the arrows. Since we're already working with a two-dimensional thing, before we get into the three-dimensional ones, let's do the third example here. So here r of t is cosine of t sine of t. And I mentioned that it's a familiar looking curve. So this one was a line. What does that other curve look like? So again, I'm going to go ahead and type in curve. Again, you can use the suggestions if it helps you, but I kind of know what I'm doing here. I'm going to type cosine of t, and note here that I do need to put the parentheses around the t here. It does want you to use function notation for sine and cosine. If you just write cosine t without the parentheses, it's not going to know what you mean. So be kind of careful about that. Actually, I'm going to say cosine of theta and sine of theta. Just because here we're working only with trigonometric functions, so we might as well use thetas. You don't have to do that. I'm just going to do that here just to illustrate it. We want to think about what values of t to put in here, or sorry, values of theta, if I'm using theta. Well, since we're working with trig functions and those are 2 pi periodic, we might as well just go from 0 to 2 pi. If you pick a bigger one, it actually will technically change what GeoGebra will show, except in this particular case, things will kind of overlap and you won't see it. So if I go ahead and plot that, what I get out here is the unit circle. Because if you think about it, cosine squared plus sine squared equals 1. So this really is just the same as the circle given by x squared plus y squared equals 1. Yeah, and it just completely overlaps. It's not really even showing any difference between them. One advantage of doing this as a parametric curve, if I only want to show half of the circle, I could go, say, from 0 to pi. Actually, I'll get this one out of the way so you can see it. So as the theta goes through its values, it starts. Actually, we could even put a of 0. Remember, a here is the name of our parametric curve. A of 0 is this point over here. If I do a of pi over 2, oh, I think I typed something in there. A of pi over 2. Yeah, there we go. So here, this is the point on the curve that you get when you plug pi over 2 into this parametric curve. And then a of pi is going to give you that point. Essentially, as you go through the values of theta, you end up going around the curve. In fact, if I went from 0 to 2 pi, you end up going around over to here. So you might notice here that theta is literally just the angle that you have with the positive x-axis. Just exactly what you do in trigonometry. But the point here is this is a handy way of working with the unit circle and not necessarily having to deal with, say, pluses and minuses and all that kind of stuff. The sines and cosines take care of all that. If I were to actually be asked to draw this curve, with arrows like the book does, I would draw this circle, and then I'd put arrows pointing along the curve in this direction, because that's the increasing theta. Alright, on to the three-dimensional examples. So recall our second example here had component functions of t squared, square root of t, and ln of t. So I'm just going to go ahead and write curve. This time I'm using the other suggestion. The first expression is t squared. Use a little caret there. That's on the 6. If Shift 6 gives you that notation. If you're not familiar with that, but I'm sure most of you are. Second one is the square root. Square root I need to write as an SQRT because we can't really we don't have a button put that actual notation, the radical notation that we're familiar with. Put of t. Natural logarithm is just ln of t. Obviously, my parameter here is t. And let's think about what t values even make sense. Since we actually have square roots in ln's, we don't want to go below 0. That won't really give us anything. And what GeoGebra does if it doesn't know how to plug something in, it will just kind of it won't put that in there at all. So I can go ahead and put 0 here. Obviously, 0 can't put into the natural log, so GeoGebra would just ignore that point. It handles it pretty well. But I do want it to go up to 0. And then let's just put in a big number like 10 and plot that. So I get this curve. Kind of goes down along the z-axis, and then comes up, and then comes off this way. Now, if you have to kind of think about exactly how it's doing that. If you don't know what values of t would correspond to what direction the t is increasing along this curve. But because we can actually plot points on this curve really easily, let's just pick a of, well, I don't want to pick 0 here, but let's just pick a of 1. A of 1 is this point here. And then let's go ahead and pick a of 2. So here t is equal to 1, here t is equal to 2, so it's pretty obvious that t is increasing in this direction. In fact, you can kind of think about what's happening at 0. If you were to try to plug in 0, the ln of t is going to give you a negative infinity. I mean, technically that's not a value that you get out of the function, but if the limit as t goes to 0 of the natural logarithm is negative infinity, and that's our z value. So we're going to negative infinity along the z-axis. And that's kind of why it seems to have an asymptote here, because it technically does, even if we're working in three-dimensional space. This line here is actually approaching the negative infinity on the z-axis. All right. Our fourth example here, we have cosine of t, sine of t, and then t over 2. So if we go ahead and just put that in here, we have cosine of t, sine of t, and if we were just to plot that part, and we could even leave that, we can go ahead and do that. Let's just type in what we had before. It will actually plot our two-dimensional curve in three-dimensional space. So here we have that two-dimensional circle, but then putting in the z component, our z being t over 2, gives us a different curve. It might be a little hard to see exactly what's happening here, but now it's kind of curved upwards. And here, because there's no trig on the t over 2 part, it actually doesn't repeat like it does for the sine and cosine. So maybe we should go ahead and pick bigger values for our limits on where t starts and where it ends. Let's just pick big ones that will ensure that it'll go off the screen, or go off the visible area of this. So let's go from negative 10 to 10. I like 10. 10 is a big number that usually goes off. If that's not big enough for something that you're looking at yourself, just pick bigger ones. You'll be able to handle it. But here, when I pick bigger t's, you can kind of see that it continues. For negative values, it continues downwards. For positive values, it continues upwards. And this curve here, actually, maybe I can get it to, sometimes it allows me to shrink this, sometimes it doesn't. Let's actually make the, I don't know, let's say t over There we go. And I guess we can even go further on this then, because I made this small. That made the z value smaller, so now I need to go further. So let's just go all out. But what we can see here is it's kind of a spiral, or in other words, what we call a helix. And it's a pretty standard, easy to work with curve that we will probably see in a lot of examples going forward, just because it allows us to do a lot of things with it without getting too complicated. I mean, we're going to be getting to some calculus where we will differentiate things. Sine and cosine are really easy to differentiate, and t over 5 is even easier. So it gives us a nice non-trivial example that we can do a lot of stuff with. So we'll be seeing the helix again sometime. Alright, and one last example. And this will be the last example for this video. I'll go ahead and make a second video for the rest of the section. But I just want to kind of put in one of the curves that the book puts in. So this is from, if you look at figure 7. This is a three-dimensional curve, and it's a little bit more complicated of a formula. So here we have our x component is 4 plus sine of 20t. You kind of have to watch the parentheses here. So I had the 4 plus sine of 20t in parentheses, but I'm going to be multiplying that by cosine of t. Then I'm going to do kind of the same thing. I have another 4 plus sine of 20t, and that's being multiplied to sine of t. And then finally, my z component is going to be cosine of 20t. Obviously, the variable here is t, and let's just go from 0 to 2 pi. If that's maybe a little not enough, we can always expand that, but that's a good place to start. And we have what the book is calling a toroidal spiral. Basically, a torus is a donut shape. You kind of take a circle and you take that circle around a particular point, kind of a circle of a circle. And here, essentially, we have a spiral that's going around that donut shape as it goes around the origin. This would be a really hard thing to write down without using parametric equations, but parametric equations give us a very easy way of writing this thing. These formulas wouldn't be too bad to work with compared to how bad it might look like it should be from our shape here. We could actually do calculus with this rather easily, in fact. And it's just one of the powers of these. If you have a good parameterization of a curve, it can make things really easy to work with. Though that's not always the easiest thing to get. So it's just nice to be able to take some formulas that we know are going to be easy to work with and see some nice shapes pop out. Alright, so again, I'm going to leave this video here, and then we'll come back and we'll discuss how we can look at various curves and get parameterizations of them, get parametric equations that give you that curve. So I'll see you in the next video.